Hello and welcome to Physics Platter. Today in Physics Platter we will be talking about heat and calorimetry. This lecture is going to be a basic lecture on the heat and calorimetry on the 9th and 10th standard, or rather secondary school standard, so that we won't be talking in so much into detail on these topics. Rather, when we talk about these topics later in thermodynamics, we will be talking in detail. Alright, in class 11 and 12 lectures. So for today's lecture, we will just talk about some definitions regarding heat and calorimetry and their corresponding units. Alright, so let's start off with heat. What heat is? As we all know that heat can only be felt. We cannot see heat, we can only feel it, right? So basically it's a form of energy that when a body absorbs, gets heated or gets hot. When the body releases heat, it gets colder. Alright, so it's a form of energy that makes a body colder or hotter. Okay, there are basically three types of heat we will be talking about. First of all, which is sensible heat. Sensible heat. What it means that the heat that the effect of which can be sensed, which in another way we can say that the heat which increases the temperature of a body or decreases the temperature of a body is called the sensible heat, because we can sense it directly or we can see it, we can feel it directly. That's called the sensible heat. Alright. Secondly, latent heat. Latent heat. What is latent heat? Latent means hidden. A heat which is hidden, something which is hidden is called the latent. So latent heat is a heat which cannot be felt directly, but which is required to change the state of a body. Alright, without changing the temperature of the body. I repeat, this heat that does not change the temperature of a body, rather it changes only the state of the body. State means there are three states: solid, liquid and gas. So this heat helps the body to change from one state to another state, a solid to liquid or liquid to gas or vice versa, and something like that. So we cannot feel this heat, we can only see the effect of this heat. That's called the latent heat. And thirdly is the radiant heat. Radiant heat. What is radiant heat? Radiant heat is the heat which travels by radiation. For example, the heat travels from sun to our earth by this process, by the radiation. In the laboratory setups or in our everyday lives, this radiant heat is something which we call a lost heat, because this heat we generally cannot calculate. Because to calculate this, to measure the amount of radiant heat, we need a very sophisticated and sensible devices, which is very difficult to achieve. Alright, so in this chapter or in the future chapters also, we will be mainly talking about sensible and latent heat. Alright, okay, what are the units of heat? CGS unit is calorie, which is defined as the amount of 1 calorie is defined as the amount of heat required to raise the temperature of pure water from let's say amount of heat, or 1 calorie. 1 calorie is defined as the amount of heat which is required to raise the temperature of 1 gram of pure water by 1 degree Celsius or 1 K. Okay, so the amount of heat required to raise the temperature of 1 gram of water, pure water, by 1 degree Celsius or by 1 K, or more specifically, the temperature has to be raised from 14.5 degrees Celsius to 15.5 degrees Celsius. That's the standard increment in temperature, 1 degree Celsius. So 1 calorie is defined as the amount of heat required to raise the temperature of 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. So that's the definition of 1 calorie. Of course, this is a very small unit. There is a bigger unit which is called the 1 kilocalorie, which is 10 to the power 3 calorie, of course, and which is defined as the amount of heat required to raise the temperature of 1000 grams of water, or rather 1 kg of water, from 14.5 to 15.5 degrees Celsius. That's called the 1 calorie or 1 kilocalorie. All right. The SI unit of heat is joule, which is written as J, and it is given as 1 calorie equals to 4.18 joule, or approximately 4.2 joule. Alright, 1 calorie is 4.2 joule. That means 1 joule is even a smaller amount of heat. Now let's talk about the definitions of some terms regarding the heat transfer by a body, or simply the heat. The terms we will be discussing about are the specific heat capacity, specific heat, the heat capacity, the water equivalence, the work equivalence, and so on. Okay, so let's start with the specific heat capacity. Specific heat capacity, which is represented as S. What is specific heat capacity? Okay, let's keep 1 kg of iron, 1 kg of iron and 1 kg of water. Let's consider 1 kg of iron and 1 kg of water. This is iron, this is water, and we keep both of them side by side in the sun, let's say. All right. After 30 minutes of heating, which one will become more hot? Which one will you feel hotter? The iron or the water? Of course, you will feel the iron is hotter than the water. Although they are kept for the same amount of time in the same amount of heat. Alright, so they were given same amount of heat, but the iron got hotter than the water. What does it mean? It means that even the same amount of heat cannot make two different materials equally hotter or equally colder. That means the iron needs less heat to become hotter, or the water needs much more heat to become hot. Alright, to change the same amount of temperature. From here, it is clear that the increase or decrease in temperature of a body depends on the material of the body, depends on the material by which the body is made of. Alright. Now, what is the factor? The factor which actually depends this increment or change in temperature is called the specific heat or specific heat capacity, and it is defined as the amount of heat required to raise the temperature of unit amount of a body or unit mass of a body by unit degree. Alright, so amount of heat required to increase the temperature by temperature of unit amount 1 gram or 1 kg or 1 pound, unit amount of a body by 1 degree Celsius or 1 Kelvin. Alright, that's called the specific heat capacity, and for water it is much more than any other material. For example, S for water equals to 1 calorie per gram degree Celsius. The unit CGS unit is calorie per gram degree Celsius. Let me write it later. Before that, the specific heat capacity for water is 1 calorie per gram degree Celsius, per gram per degree Celsius, and for water, for iron, it is 0.4 calorie per gram per degree Celsius. That means the specific heat capacity for water is much more than the specific heat capacity for iron. That's why it needs much more heat to change equal amount of temperature for water. That's why the water is a good cooling agent. Water is good cooling agent because it can absorb much more energy than any other material before it becomes really hot. Alright, that's why it is used as a cooling agent. That's why if you burn some part of your body or somehow you get burned from anything, immediately put water into it, right? Okay, now let's talk about the unit. CGS unit of specific heat capacity is, as we have already told, calorie per gram per degree Celsius, and SI unit is joule per kg per Kelvin. Alright, joule per kg per Kelvin, that's the SI unit of the specific heat capacity. Alright, now let's consider a body of mass m, any body whose specific heat capacity is S, and the temperature, initial temperature is T1, let's say, and we want to increase or decrease, let's say increase the temperature to T2 Kelvin, T1 degree Celsius or T2 Kelvin. Generally small t is used for degree Celsius for CGS unit, and capital T is used for the Kelvin MKS unit. Alright, now how much heat is required for this body to increase this much of temperature? We will calculate that. From the definition of specific heat capacity, what do you know? That to increase the temperature, the amount of heat required to raise the temperature 1 gram of the body by 1 degree Celsius is how much? S calorie, right? That's the definition of the specific heat capacity. Alright, so to increase the temperature, the amount of heat required for 1 gram of the body by 1 degree Celsius is S calorie. Okay, so for m gram of the body by 1 degree Celsius is how much? We need m S calorie. Alright, so for m gram of the same body by T degree Celsius equals to is m S T calorie, where T is equals to T2 minus T1. Alright, the difference in temperature. Okay, that means if the temperature, the heat required is Q, then Q equals to, we can write m S T, which we can write m S T2 minus T1 or m S delta T calorie. So the equation for amount of heat required to raise the temperature of any body of mass m by T degree Celsius or by temperature T is given as m S delta T calorie or m S delta T joule. Alright, that's a very important equation for the amount of heat required to change the temperature of a body of mass m or of specific heat capacity S. Alright, and this is also the basic equation for the calorimetry when the temperature is increasing for a body. Okay, That's the specific heat capacity, and this is also very important to solve the problems. Alright, we will talk about the problems later. Alright, next is heat capacity. Next we will be talking about heat capacity. What does it mean? Now, specific heat capacity, we have calculated that heat required to increase the temperature of unit mass of a body by unit degree Celsius, right? Similarly, heat capacity is the amount of heat required to raise the temperature of a body, not just unit mass of the body, but any mass of the body. It is just the body, not just unit mass, it is the whole body. So, the amount of heat required to increase the temperature of a whole body by how much? 1 degree Celsius or 1 Kelvin. That's called the heat capacity. Alright, and it is given, the unit is of course CGS unit is calorie per degree Celsius, because it is for 1 degree Celsius. Alright, SI is, for SI it is joule per Kelvin. Alright, the heat capacity is generally represented as C, and it is given as C equals to ms. Delta T is 1 here, so simply ms calorie per degree Celsius or joule per Kelvin. Alright, that's the equation for heat capacity. The next term we will be talking about is water equivalent. Water equivalent. Water equivalent, what it means? Of course, from the term itself it is clear that it has something to do with water. Equivalent, let's say a body of mass capital M, any body, anything of capital M is there, and to increase 1 degree Celsius of the body, we need a temperature Q, or a heat Q. Okay, so this Q amount of heat is required for M mass of the body to increase the temperature by 1 degree Celsius. Alright, now this Q amount of heat, if we take some amount of water, let's say some amount of water, and if we apply the same amount of heat Q to that amount of water, such that the temperature of this water also increases by 1 degree Celsius, then the mass of this water is called the water equivalence. If the mass is M, small m, then this small m is called the water equivalent of this body. So, what is the definition here? Definition is the amount of water. Of course, this is the mass of the water. It is given by the mass of the water M. So, the mass of the water, or the amount of water, the amount of the water equivalent is given as the amount of water whose temperature is increased by 1 degree Celsius by an amount of heat which increases the body, the temperature of the body by 1 degree Celsius. Alright, that means here Q equals to, for the body equals to, if the, let's say this is the specific heat capacity is S, and specific heat capacity for water is of course 1 in CGS. So, Q equals to, for the body, M S T, T means 1 here, and for the water is Q equals to M into 1 into 1, right. Now, this both amount of heats are same, that means we can write Q, this is let's say Q1, this is let's say Q2, then Q1 must be equals to Q2, which gives small m equals to capital into S, gram in CGS and kg in SI. Alright, so that's the equation for the water equivalent of a body. Alright, m equals to ms, here mass, m is the mass of the body, not of the water, mind it, this is the mass of the water. Alright, so that's water equivalent. It is actually given as ms by 4.2 into 10 to the power 3 kg. Alright, so the next thing we will be talking about is the work equivalent. The work or mechanical equivalent of heat. Mechanical equivalent of heat. It is clear that heat and heat is a form of energy, right? So mechanical energy can also be transferred, can also be converted into heat. Okay, for example, if we rub our thumbs together for some time, it gets hotter, right? That's how we warm ourselves sometimes in winter. So if you rub your palms or hands together, then it gets hot. Okay, that means the with the palms or with the hands we are doing mechanical work, but what we are getting is heat. So we are actually converting the mechanical work to the heat energy. All right, now if we the longer we rub, more heat we get. That means the amount of heat we are getting here or amount of work we are getting here is directly proportional to the amount of work we are doing, right? So we can write that W, the amount of work, is directly proportional to the heat energy. Alright, or vice versa, the heat energy produced is directly proportional to the work we do. Or we can write JW equals to JH. This J is called the Joule's constant. J is called the Joule's constant or mechanical equivalent of heat. This J is also called the mechanical or work equivalent of heat. Alright, this actually comes from the first law of thermodynamics, which we will talk about in detail when we talk about thermodynamics in class 11 and 12. Alright, by the way, we will start the class 11 12 class lectures very soon, and then we will get regular videos, so don't miss the lectures right from the beginning. Alright, okay, so that's the Joule's equivalent, Joule's constant or mechanical equivalent of heat, which gives us J equals to W by H. So J is the mechanical equivalent of heat, and which is given as J equals to W by H. From this equation we can define J as, if H equals to 1, then W equals to J, of course. Then the J can be defined as the amount of work done to produce unit amount of heat. Alright, so the mechanical equivalent of heat or the work equivalent of heat is defined as the amount of work done to produce unit amount of heat in a body. Alright, so that's called the J. In CGS, the value of J is 4.2 into 10 to the power 7 arg per calorie, or 4.2 joule per calorie. In SI unit, both work and heat are measured in joules, so basically it is unitless in SI and the value is 1. Okay, next we will be talking about the latent heat. So far we were talking about the sensible heat, that means the heat which was responsible to increase the temperature or decrease the temperature of a body. This time we will be talking about the latent heat, which is not actually sensible but which is visible by the change of state of the body, solid, liquid or gas. Okay, so basically, as we have already defined latent heat, it is the heat required to change the state of the body without changing the temperature of the body. Alright, let's say if we boil, before I discuss one question, The question is, I have some pure water. Alright. Question is, can you heat the water so that the temperature of the water goes to 110 degrees Celsius? Is it possible to make the temperature of a pure water 110 degrees Celsius? Is it possible? Questioning. So what happens? If we heat the temperature, what happens? The temperature of the water goes increasing from, let's say, from room temperature, which was 30 degrees Celsius, to 50 degrees Celsius, to 60 degrees Celsius, to 90, and then what happens to 100 also? It reaches to 100 degrees Celsius, and then what happens? Does it go to 101 degrees Celsius? No, it starts boiling. It starts boiling at 100 degrees Celsius, because the boiling point of water is 100 degrees Celsius. What is the meaning of boiling? Boiling is a process in which the whole system of a liquid changes its state from liquid state to the gaseous state without changing the temperature. At the time of this, remember, at the time of changing the state of a body, the temperature does not change. The temperature remains constant. Alright, because the heat that is given to the system is completely used for changing the state of the body, because we know the liquid, the intermolecular distance of liquid is smaller than the gaseous molecules, right? Gaseous intermolecular distance, which is something like this. Okay. So we need, of course, some energy to be given to the liquid to increase the intermolecular distances, and that energy is, of course, given in the form of heat, and vice versa. If we want to change the state of the gaseous molecules to the liquid, we have to take away heat from the body. Alright. This heat which is required, which is used to change the state of the body, is called the latent heat. Is called the latent heat, and is given as L. Is given as L. Now, for different change of states, this value of L is, of course, different. For example, for a same body, same material, for water, let's say, the latent heat for melting from solid state, from ice to liquid, which is melting, of course, and the temperature has to be 0 degrees Celsius and has to be constant, and the L for melting of ice is given as 80 calorie per gram. 80 calorie per gram. And for freezing also, this way it has to be freezing. Freezing also, it has to be melting, and freezing, it has to be 80 calorie per gram. And for boiling, from water to gas to vapor, it is, of course, boiling, and the latent heat for boiling of water is given as 537 calorie per gram. Alright. So latent heat for freezing is 80 calorie per gram for water, and latent heat for boiling is 537 calorie per gram for water. Okay. So that's the latent heat required to change the state of a body. Alright, now we'll quickly talk about graphically how it looks. Let's say we take some amount of water, m gram of water, or rather, let's start from solid itself. Let's say we take m gram of ice cube. We take an ice cube whose mass is m gram, let's say, okay, m gram. Now we, the temperature is, let's say, -5 degrees Celsius, temperature is minus 5 degrees Celsius. Now we want to convert this to vapor of 110 degrees Celsius, let's say. What do we have to do? Of course, we have to apply heat. We have to apply heat to the ice. But will it go to the, will it become the vapor immediately? Of course not. What are the processes? First of all, from minus 5 degrees Celsius, this ice will come to another 0 degrees Celsius. M gram of ice, m gram of ice at 0 degrees Celsius. For that we need heat, of course. All right. Then it will become liquid at 5 m gram of liquid at 0 degrees Celsius, where we will need latent heat. All right. Latent heat for freezing, LF, let's say, or melting, LM. Let me write LM here, or 80 calorie per gram. All right. Then from water, it will become water at 0 degree centigrade to water at 100 degrees Celsius, m gram of water at 100 degrees Celsius. All right. For that we again need heat. And then from 100 degrees Celsius of water to 100 degrees Celsius of gas, 100 degrees Celsius of vapor, of the m gram of vapor, which again needs latent heat, and from 100 degrees Celsius gas to 110 degrees Celsius vapor. Again we need some heat here. So in this process the ice changes its state twice, first solid to liquid and then again liquid to the gas, and in the meantime in the same state it also changes its temperature, the temperature increases. All right. So in the whole process we will try to see in a graph what happens. First of all, let's see, let me draw a graph like this. This 0 x axis we represent the time, and t axis y axis we represent the temperature theta, let's say. All right, theta degree Celsius. 0, and this is minus temperature. Let's say this is somewhere here is minus 5 degree, minus 5, and somewhere here is let's say 110 degrees Celsius. Okay. The water at time t equals to 0, the ice was at minus 5 degrees Celsius, and then we start heating the ice and the temperature becomes 0 degrees Celsius after some time. All right. And then when it reaches to 0 degrees Celsius, it starts changing its state. The ice starts melting. The ice starts melting and it becomes the same amount of ice for 0 degree Celsius. Okay, so it changes the state, and then after some times it becomes completely liquid at the 0 degree Celsius, and then it's the temperature of the liquid starts increasing, and it increases, it's a straight line of course, it increases to a temperature 100 degrees Celsius. This is 100 degrees Celsius of water. All right. And then at that temperature 100 degrees Celsius, the water starts boiling and it remains, the temperature remains constant for some time until the whole water becomes vapor. And at some time at this point, let's say the whole water becomes vapor, and once the whole water changes its state from liquid to the vapor, the temperature again starts increasing. Okay. And after some time the temperature of the vapor becomes 110 degrees Celsius. Okay. So let's say the body started at the initial point is A, this is B, this is C, this is D, E, F. Alright. So, from A to B, the temperature of the ice increased from -5 to 0 degree Celsius. From B to C, the temperature remained constant, but the whole ice melted to the same amount of water. And then from C to D, the temperature of the water increases from 0 degree Celsius to 100 degree Celsius, keeping the mass same. Of course, the mass remains constant for the whole process. And then from D to E, at point D, the water starts boiling, and from D to E, the whole water changes from liquid to vapor. Alright, at point E, the whole water becomes vapor, and from E to F, the temperature of the vapor increases from 100 degree Celsius to, this is 100 degree Celsius to 110 degree Celsius. So, in this process we can say that 1, 2, 3, 4, 5 changes. So, we can write from A to B, let us say the Q1 amount of heat required, and this will be given because here the temperature only increased. Here the temperature only increased, that means Q equals to M S delta T will be the equation for this one, delta T1, let us say here, okay, for Q1, here A to B. Then from B to C, here only the state changed, but the temperature remained constant, that means del T is 0 here. Alright, in this case we can write the amount of heat required to change the state of the liquid to the gas is of course the latent heat. Alright, now L, here one thing we didn't discuss is that this latent heat L is given defined as the amount of heat required to change the state of the body from unit amount of the body to change the state, right. That means for m gram, for 1 gram of liquid we need L amount of heat to increase for 1 degree Celsius, sorry, not 1 degree, of course the temperature remains constant, to change the whole state, the state of the whole body. For m gram of the body, to change the state, how much heat we need? Of course ml calorie. Okay, so that means here from B to C, the liquid becomes vapor. That means here we will apply the formula ml freezing or melting, mlm. Alright, so this is the amount of heat required for the ice to become the liquid, become complete water. Then from C to D, again the state does not change, but the temperature changes. That means at this point we will apply the formula Q3 equals to ms delta T2. Okay, so first this was the specific heat capacity for ice, and then this is the specific heat capacity for water. Mind it, this is for the ice. Let me write I here, this is W. Okay. Alright, then from D to E, here also the temperature does not change. What changes is the state of the body, and the whole water becomes gas, vapor. That means here we will apply the formula for the latent heat, which is ml, here the latent heat for boiling, mlb. Alright, and then E to F, the temperature increases, the state remains the same, which is the gaseous state, and the total heat required Q5 equals to how much? Q5 is equals to ms delta T3 here. Delta T1 was -5 to 0 degree Celsius, that means 5. Delta T2 is 0 to 100 degree Celsius, that means delta T1 here is 5. Delta T2 equals to 100 degree Celsius, and then delta T3 equals to 100 to 110, that means 10 degree Celsius. Alright. Okay, so which means if we want to calculate the total heat required for the ice to go to the 110 degree Celsius of vapor, we will have to add up all the required heats. That means Q1 plus Q2 plus Q3 plus Q4 plus Q5. Alright, which is, if we add all the heats, we can simply find the total amount of heat required to increase the temperature of m gram of ice at 5 minus 5 degree Celsius to m gram of vapor at 110 degree Celsius. Alright. By the way, this process, the process that I have just discussed to calculate the amount of heat, is very important to solve the problems in calorimetry. Alright. This is a basic formula for the calorimetry. What is calorimetry? Calorimetry is the branch of science, a part of science in which the amount of heat is basically measured. The heat is measured basically. Calorie is represented for heat, and metry is of course comes from meter, which is something in which we can measure. The device is called the calorimeter, of course. Alright. So calorimetry is a branch of science in which we can measure the amount of heat. How do we measure it? Basically we measure it by the transfer of heat from one body to another body, and we apply this formula. When the temperature of the body is changing without changing the state, we apply the formula Ms delta T or delta small t, and when the temperature is not changing, only the state of the body is changing, we apply the formula Ml. Okay, so these are the two formula that we apply to measure the calorimetry. Now, few things regarding calorimetry. Of course, the most important thing is the principle of calorimetry. There are some principles, of course, followed in calorimetry. What are the principles? Before going to the principles of the calorimetry, we must talk about what is calorimeter. Calorimeter is basically, we will discuss about these things in much more detail when we talk about the same things in class 11th and 12th level. Mind that this is just a class 10th or 9th level lecture, so we will very roughly we will talk about the overview of this device, and then we will whatever is required for this standard. Alright. So calorimetry is a device made of metal which is covered in a very isolated box, which is thermally very much isolated. Alright, that means it cannot release energy to the heat to the environment, or also it cannot take energy or heat from the environment. Alright, there is a metal stirrer or something which looks like spoon, by which we can stir the mixture inside. Alright, generally there is water or calorimetric liquid, and then a body which is whose specific heat capacity or some other thermal terms are to be determined are there into that water. Alright, and the heat transfer of the body to the water or from the mutual heat transfers are calculated, and then corresponding terms are calculated by applying the formula. Now, there is of course some principles to be followed in this calorimeter. What are the principles? First principle is that no transfer of heat, no transfer of heat with the surrounding. That means nothing to the surrounding, or nothing, rather better to say nothing out of the system, and nothing into the system. No exchange of heat with the surrounding. No heat goes inside, no heat from inside comes outside. That's absolutely prohibited. So that's the first principle. Second principle is what? Second principle is that no chemical reaction is happening. No chemical reaction. No chemical reaction must happen between the materials. Alright. Thirdly, no solution is formed. No proper solution is formed between the materials that we use in calorimeter. Alright, so these are the three principles. Basically, there are two principles in the first point. Nothing goes out of the system, no energy comes into the system. No chemical reaction between the materials, no solution is formed between the materials. Alright. Okay. Last but not the, so these are the principles of the calorimetry. The calorimeter is used on the basis of these two formula and these three principles. And last but not the least, we must talk about something which is very important, and that's called the thermal equilibrium. What it means? Thermal equilibrium. What is the meaning of thermal equilibrium? Two bodies are said to be in thermal equilibrium with each other when the temperature of the bodies are same. If the temperature of the first body is T1, if the temperature of the second body is T2, then they are said to be in thermal equilibrium only when T1 equals to T2. Why is it like that? Generally, two bodies are said to be in thermal equilibrium when there is no heat transfer, no heat exchange between them. No heat exchange between them, and that happens only when the bodies are at the same temperature, because when the bodies are at different temperature, that means a body is cooler and the other is hotter. Then if we bring them in contact with each other, then of course the cooler body takes the heat from the hotter body. How long? Until the temperature of both the bodies becomes same, and at that point this heat transfer stops, and at that point it is said that the bodies have reached the thermal equilibrium. Alright, and this is very important for the calorimeter also, because in calorimeter we have to wait until the thermal equilibrium is achieved between the systems, between the materials. Alright, so these are the things that we have talked about in this chapter. In the standard of class 9th and 10th, we will soon be starting class 11th and 12th classes of physics. So keep following my lectures. If you want to follow the further lectures, subscribe to the channel, so that also click the bell icon so that you don't miss any new videos. Alright, again I'm telling you, soon class 11th and 12th classes will be starting. The lectures will be starting from next week probably. There will be regular videos uploading in this channel on these chapters, so don't miss them. Subscribe to the channel, click the bell icon, and if you have any queries or suggestions, please write me in the comment section, and I will try to come back to you in the next video with the answer. Alright, so see you in the next video. Till then, take care.